Hello, I'm Anna Hankin. I'm a lecturer in the Department of Chemical Engineering at Imperial College London, and for some years now I've been working on developing a better understanding of semiconductor liquid interfaces and how to model them. So the original purpose of the work was to express mathematically both the dark and photocurrents at such interfaces as a function of applied potential. So with the aim to develop kinetic equations that could be input into multiphysics models for optimizing the engineering of photoelectrochemical reactors. But on the way to doing this, we ended up hitting some stumbling blocks in that we were unable to use any of the existing models to actually explain the experimental data we were getting. And by that I mean simple voltammetry data. And so we ended up revisiting a lot of the literature published in the 70s and 80s and identifying some of the assumptions that were made at the time, assumptions and simplifications, that have since been simplified further and further for the analysis of interfaces that we use today. And so in this talk, I'd like to recap some of the important concepts that are perhaps being forgotten in the modeling and treatment of semiconductor liquid interfaces. So to start off with, on this graph, what we have is a fairly typical voltammogram that's been recorded on a semiconducting photoanode in aqueous media. So we have what's called a dark current, which is measured when the interface is not irradiated by light. And then we have the total current in black, which is recorded when the photoelectrode is irradiated. And then, because the total current is a sum of the photocurrent and the dark current, we can obtain the photocurrent by subtracting the dark current from the total current. And the photocurrent is shown in red here. And what is noticeable from this particular result is that the dark current is not always non-negligible on the scale of applied potentials that's relevant to photoelectrochemical applications, so water splitting. So for the photocurrent, there are very significant differences between the photocurrent that is predicted theoretically at the semiconductor liquid interface and the photocurrent that is actually extracted. The theoretical prediction, which is based on the Gärtner-Butler equation, doesn't take into account the typical loss processes. So the two main ones are bulk recombination, in which the photogenerated charge carriers recombine in the bulk of the semiconductor, and this process decreases the photocurrent by a constant factor. And then there's also surface recombination, which takes place in the space charge layer. So the recombination is a function of the applied potential, and it is highest at small band bending. So recombination is highest near the flat band potential, and then as band bending increases, the rate of recombination decreases. And so the question is how to go from the theoretical prediction to a prediction that is actually representative of the experimental measurements on our electrodes. The original prediction of the photocurrent is a combination of models developed by Gärtner and Butler, and so the combined prediction is termed the Gärtner-Butler equation, and it predicts the photocurrent as a function of band bending, which is this delta phi SC here, on the very right, and parameters including the dielectric constant, doping density, as well as the absorption coefficient of the material. Now, in the original formulation, this equation was for monochromatic light, but it's possible to apply it to white light by taking the spectrally resolved value of the product of the absorption coefficient and incoming light intensity measured at each wavelength. And so that's what's shown here. Next, this equation is missing some important terms that could make it more realistic, and so there are some corrections that could be made. This first correction is the inclusion of light attenuation by all the components in the electrochemical cell that attenuate light between when it impinges on the outside of the reactor and when it actually arrives at the surface of the semiconductor. So these components can include the electrolyte and the optical window, and the effects of these can be determined both theoretically and experimentally. So next, the corrections have to be made for the two efficiency terms that we discussed before, and these can both be determined experimentally. So the phi surface is the charge transfer efficiency. So this is the rate of the charge transfer at the interface over the total rate of charge carrier generation. And this can be determined using photoelectrochemical impedance spectroscopy. And then there is the bulk charge transfer efficiency, which can be determined experimentally from voltammograms recorded in the presence of a scavenger and in the absence of a scavenger. Now, finally, as in any electrochemical kinetic equation, you can impose a mass transport on the function, and in this case we are limiting it by the photon flux, which is here in the denominator of the equation. This is an example of model predictions we published earlier using experimentally determined parameters for our undoped hematite photoelectrodes operating in alkaline media. So for our electrodes, we determined the flat band potential, using which we then determined the doping density of the semiconductor. We measured the absorption coefficient of the material as a function of wavelength, and we performed some optical measurements to determine the attenuation of the incident light by the optical window and the electrolyte in our cell. We carried out photoelectrochemical impedance spectroscopy to determine the interfacial charge transfer efficiency, which we then modeled using a mathematical expression. And finally, we imposed a photon flux limitation on the total current, and the results were in very good agreement with our experiment. The impact of surface recombination can be seen when we compare the results of kinetics measured in the absence and presence of a Hall scavenger, so in this case hydrogen peroxide. So we can see that the curve with the hydrogen peroxide looks much more like the theoretical prediction, and that it does not have this typical S shape that's symptomatic of high recombination rates near the flat band potential. One of the stumbling blocks we hit when we did our models was the identification of the flat band potential of our electrodes. So the flat band potential is an extremely important parameter, interfacial parameter. It's a reference state relative to which photoelectrochemical kinetics may be assessed. But the assumptions made during flat band potential determination from various measurements, including interfacial capacitance, have led to an implausibly wide range of values being reported for essentially the same material. And we can show this here on the electrode potential scale. So let's draw an envelope of the water splitting potential of 1.23 volts. So the reversible potentials are here for water oxidation and water reduction at pH 14. And so where is the flat band potential of hematite? Now, if we collect a wide range of literature values, which have mostly been obtained from Schottky plots, we get a spread of over 0.8 volts. And then from our own study, which we published about 2 years ago, we showed that actually if you use a multitude of techniques to determine the flat band potential, you can get whatever value you want, and it practically spans the whole water splitting potential range. So what did the techniques actually give us? So we used open circuit potential measurements to try and determine the flat band potential. So we did this without scavenger and with hydrogen peroxide scavenger. And we got values that were quite close together, but these values were subsequently superseded by other experiments that showed that the flat band has to be more negative. Schottky plots, which we did diligently and with multiple repetitions, also had a very wide spread, and then we extracted the flat band potentials from chopped photocurrent data, which we did with and without Hall scavenger, and these results were we believe we're the most trustworthy of all. And then we also perform photocurrent squared, so using the Gärtner equation, to determine the flat band potential without a scavenger and with a scavenger. And so it's the result without the scavenger that really is the least correct one, because it essentially gives you the kinetics of water oxidation, which are known to be poor. So this has to be corrected for recombination and so on to back calculate the flat band potential value. But essentially the values are all over the place. And part of the reason is that the analysis of experimental data for flat band potential determination often excludes the contribution of the Helmholtz layer to the experimentally determined results. Now, the Helmholtz layer is usually entirely excluded from models of the semiconductor liquid interface because it is assumed that the potential drop across the Helmholtz layer is negligible and that all of the applied interfacial potential is dropped across the semiconductor. But this is not necessarily true and depends on many things, but critically so on the doping level in the semiconductor. Now, the more metallic the semiconductor becomes, the greater the degree of potential that's dropped across the Helmholtz layer, because when you have a metal liquid interface, the entirety of the potential drop is dropped across the liquid, and hence this must be borne in mind when analyzing semiconductor liquid interfaces without prior knowledge of the doping level of the semiconductor. Indeed, we show the contribution of the Helmholtz layer here in the model of how the applied potential is distributed between the semiconductor and the Helmholtz layer. So on the x-axis, we have the total interfacial potential comprising the semiconductor drop and the Helmholtz drop. And on the y-axis, we have the fraction of that potential that's dropped across the Helmholtz layer. And we can see how significant the drop is, particularly for highly doped semiconductors in the state of depletion, which is common for the operation of the n-type semiconductor. This is just another way of showing the same thing as was shown on the previous slide. So on the x-axis here we have the semiconductor potential, and on the y-axis we have the actual total interfacial potential that has to be applied in order to achieve the potential drop across the semiconductor. So, for example, when we have a doping density of 10 to the 24 per meter cubed, we can see that there is a fairly straight line between the two. So, in order to obtain a semiconductor potential drop of just over of 1 volt, we need to apply a little over a volt, so about 1.1 volts. So, in this case, not much of the potential is dropped across the Helmholtz layer. However, when we have a very highly doped semiconductor, so approaching degeneracy in this case, so 10 to the 26 per meter cubed, we can see that in order to achieve a band bending of 1 volt, we need to apply a total potential across the interface of almost 1.8 volts, so a very significant difference. So in addition to the changes in the contribution of the total applied potential that goes towards the Helmholtz drop, we must also not forget that even at the flat band condition, when no current flows, it doesn't necessarily mean that the potential drop across the Helmholtz layer is 0. So we discussed this in a publication published quite a few years ago in Phys-Chem-Chem-Phys, which is that the potential drop across the Helmholtz layer at the flat band condition depends on whether the pH of the solution being used for the experiment is higher or lower than the pH of 0 charge for the material. So for example, if we have hematite and it's immersed in alkaline media, such that the pH of our electrolyte is higher than the pH of 0 charge, we actually have a positive potential drop across the Helmholtz layer even at the flat band condition. And then once the band bending is actually allowed to take place, we can see that the total interfacial potential drop consists of contributions from the Helmholtz layer and the band bending across the semiconductor, which is the space charge layer. So from the results that we've seen in the last few slides, we can see that as the total interfacial potential is modified, the ratio of this total potential that goes towards the semiconductor and the Helmholtz layer also changes. And without modeling this, it's very difficult to interpret experimental results. So the potential drop in the Helmholtz layer is important not only for modeling of photocurrents, but also of dark currents. Now, dark currents can be assumed to flow via quantum mechanical tunneling of electrons from the reduced state in the electrolyte and the conduction band in the semiconductor. Why? Because for dark currents to flow, normally you need a very high band bending, and the barrier is too high to be overcome by thermal activation. And electrons instead tunnel through the space charge barrier, and this becomes easier the more heavily doped the semiconductor is, and the higher the degree of band bending, which tends to thin the space charge layer. Now, they have to be a set of conditions under which the tunneling is possible. So, for example, in this schematic, it shows that the bulk of the conduction band, the potential of this bulk is higher than the redox potential in the electrolyte, which means that the space charge layer has a finite width, and the width at the level of the redox potential is the tunneling distance for the electron. And this shows the condition under which tunneling is not possible, because the potential of the conduction band bulk is less positive than the reversible potential of the redox species in the solution. So from the literature we can see an example of the potential dependence of the anodic currents at highly and moderately doped, in this case zinc oxide electrodes, with and without the addition of a reducing agent. So the onset for the dark currents in the highly doped semiconductors, so here 10 to the 20 per centimeter cubed corresponds to our case of 10 to the 26 per meter cubed. So the onset of dark current for these highly doped semiconductors is much earlier than for moderately doped semiconductors. And the reducing agent, so for example hydrogen peroxide or anything else, has a bigger contribution to the highly doped case. And through our modeling we begin to see why. So using equations developed in the 70s and the 80s, we can model the tunneling distance for electrons coming from the reduced state in the electrolyte into the conduction band of the semiconductor as a function of the overall interfacial electrode potential that has been applied. And we can see that until a certain potential, the tunneling distance is irrelevant, and that is because it is forbidden. So, which means that the conduction band bulk potential is still lower than the redox potential, and only after the conduction band bulk potential moves past the redox potential does tunneling become possible. And subsequently, as the electrode potential is increased, the tunneling distance decreases, and in terms of magnitudes we can see that the tunneling distance is considerably smaller for highly doped electrodes. And this is just to zoom in on the highly doped case to show that the tunneling distance is well below 5 nanometers, so very small. So the graphs I just showed in the previous slides, the electrode potential includes in it the contribution of the Helmholtz layer to the distribution of the applied potential between the semiconductor and the Helmholtz layer. Now, the new dotted line graphs show what the predictions would have been if the model had ignored the contribution of the Helmholtz potential drop. So it shows that dark currents for both, for all of the doping levels, are predicted to start much earlier. And this is particularly significant for the highly doped case. But this highlights that the exclusion of the Helmholtz layer results in somewhat unrealistic predictions. So finally, we were successful in some initial attempts at modeling dark currents measured in our system versus a mercury oxide reference electrode. So we used the kinetic equation developed by Meming and Méliès, and we were able to identify an exchange current density for electron transfer, which resulted in a very good replication of our experimental data. So the task ahead for us is to gather a body of experimental data for dark currents measured under different conditions, different pHs and electrodes of different doping densities, to see if we can prove the reproducibility and the applicability of our model. And so this prediction of the dark currents is then combined with a prediction of the photocurrents to predict the overall performance of the electrode. And it is these models that we will use in our ComSol multiphysics models for modeling reactor performance when you have several semiconductor liquid interfaces in the solution, and perhaps PVs and other experimental components that also contribute to the performance of the system. Finally, these are details of the Electrochemical Systems Laboratory, which is based in the Department of Chemical Engineering, where we collaborate with our colleagues in the departments of chemistry and the departments of physics for many contributions to these interesting discussions. And if you'd like to get in touch with us about this topic or anything else, we'd be delighted. Thank you.